Okay. Jason, you had a question, or I wasn't saying anything. So some people can still hear me. What if I turn this? No. Oh, the speakers are muted for me. Okay. All right. All right. So maybe we'll get started. At least some people can hear me. Whoever that was, I guess that was Jason. I could hear pretty well. Oh, okay. So you're talking about, you can see my screen share, right? You can see this, right? You're talking about this problem here? All right, so this is assignment 1, question 2. All right, we have 4 masses. 1, 2, I don't remember how I labeled them in the problem, and they're separated by inextensible mathless rods of length L. So the rods don't participate in the system. I mean, in the sense that they don't have any mass, so they don't contribute a moment of inertia. So what you're actually asked to find is the kinetic energy, right? Which we'll call T. And so T is going to be the sum over of a half m vi squared, where v is the speed of each of these guys, right? So if you don't reduce the number of degrees of freedom and you introduce a x and y coordinate system, this vi squared here for each coordinate, for each mass, is its x position dot squared plus its yi dot position squared, right? So if we just think of it, the number of degrees of freedom, so it's a 2-dimensional problem, right? So the maximum, so there's 4 particles. So the total numbers of degrees of freedom without the constraints, 2n, is equal to 8. It's 2 instead of 3 because it's 2-dimensional problem instead of 3-dimensional, right? So in principle, there's 8 degrees of freedom. Now there's 4 constraints provided by these rods, right? And now you have to think about the system physically. So if you have 4 rods, and you can imagine the rods as being hinged on the masses. And each rods can change, but it's still constrained. Like let's say you only had 3 masses and you had 3 rods of fixed length, the masses would actually not be able to move, right? The angles can't change because a triangle is defined by 3 fixed lengths, and so you can't change the angles. However, if there's 4 corners, and you have the constraint that the lengths are fixed and that these are hinged, these angles can change, right? Because you can imagine one system or one configuration is a square, and then you can press 2 of the masses towards each other, and in principle make a not square, right? So because of these constraints, now there's 4 rods, so each rod provides a constraint, and that constraint is that the distance between any 2 masses is fixed, right? So you have, for example, x2 minus x1 squared plus y2 minus y1 squared equal L squared, right? That's a constraint. Yeah, a question or? Then you're asked in the problem to find. So there's 4 constraints, right? And so really, the numbers of degrees of freedom is 8 minus 4, so it's equal to 4. So you really only need 4 generalized coordinates to describe the system, right? So then you have to figure out a clever choice of generalized coordinates. So what this means is you only need to specify 4 numbers to completely specify the location of the system. And so, that's the part where you guys have to think about it a little bit. But, you could, for example, so you get 4 generalized coordinates, which will be Q1, Q2, Q3, and Q4. And the choice that I used was that Q1 and Q2 was X1 and Y1. Sorry. So in principle, you can specify the position of one mass, and then maybe some angles that will give you the position of the other masses. So what you get after that is you get a set of equations. Okay, so then where you convert all the x1, 2, 3, 4s and y1, 2, 3, 4s into the q1, q2, q3, q4. So I used q1 and q2 to be x1 and y1. Okay, so then x1 is equal to x1 and y1 is equal to y1, sure. But then you have x2, for example, is going to be some function of q1, q2, q3, q4. Remember, q's, i's, are the generalized coordinates, right? And they depend on time. So once you figure it out, how the x position of this guy depends on the xy position of this guy plus some angles, and you can use symmetry that you've discussed, for example. What you then need to find is x2 dot, right? And x2 dot is going to be di x2 by di q1, q1 dot, chain rule, di x2 by di q2, that's a q2, q2 dot, plus di x3, oh, sorry, di x2 by di q3, q3 dot, plus di x2 by di q4, q4 dot. Alright? So step 1, figure out what's a good choice of these q's. Step 2, write out all the coordinates of these guys in terms of the q's. What step was I on? Step 3, write out the time derivative of these coordinates with the chain rule. And then step 4, or whichever step I'm on now, you want to get T is the sum of the m's, so they're all the same masses, so I can move them out of the xi dot squared plus yi dot squared, right, where this is ei squared. So first you have to express the coordinates of all of these guys and their time derivatives in terms of the q's. So now this is in terms of the q's, and then you can finally write out the kinetic energy. So you're going to have to square these things. So it's a lot of math and algebra. But you'll find some cancellations. If you use the angles, then you'll have sine squares plus cos squares. And then you're going to end up with some really long expression in terms of the Q1's dots, Q2 dots, Q3 dots, and Q4's dots. And in principle, it's also in Q4. So does that sort of answer your question? That's sort of an outline of how to approach it. Yeah, so you don't need the moment of inertia, right? The Okay. Yeah, because you can't model the system as a whole, right? Because you could do the moment of inertia of four balls connected by rods, but the problem is the balls can move with respect to each other. So you can't do the moment of inertia of the whole system. You have to consider each ball or mass as its own entity. And then the moment of inertia is just a way of doing the kinetic energy or the effective mass of a bunch of point masses. So you don't need the moment of inertia. Any more questions about the assignment? It's actually a lot of math. I'm sorry. The first assignment is all basically writing out very long equations to get you into the mood. You do need to specify the QI, right? You should write in the you should make it very clear in the assignment what you've chosen as your four generalized coordinates. And so the example that, what I chose was I chose the x and y position of these guys, of one mass as Q1 and Q2, and then I chose a couple of angles that specify the rest of the system. And then you can write out these equations here for x1 and x2 as a function of the q's by using some of the symmetries. Okay, so let's make this the real page one. So let's start with well, if you have more questions about the assignment, feel free to ask me. Otherwise, I'll start with a review of the last time. And the main point that we found is that we want the stationary um, point of an integral. So we had an integral I, which was evaluated between fixed points, so it's a definite integral, of some function L that depends on y prime, and x. And the goal was to find y of x such that I is stationary. Okay. And then I motivated physically why we wanted to do, for example, the problem. If you have the so-called brachistochrone, where you have some wire that starts at point A and ends at point B in the xy plane, where y is vertical, so we have gravity going down, and we have some bead. We saw last time that the time that it takes for this bead to go from A to B is an integral that depends on the shape of the wire. And so that gave us an example of a problem where you have the integral of something and you want to find the function where the integrand depends on that function, and then the integral is stationary. In this case, we wanted to find a minimum. Okay? And so the key constraint here was that the wire was fixed to be between A and B. And then, of course, we'll see that all of classical mechanics is, in fact, based on the foundation that some integral behaves this way. And I guess the other point was that y prime is dy by dx, right? So let's recall again the variation. One could define a new function, y bar, which was y of x plus epsilon phi of x, right? So we make a completely new function, y bar, that differs from y of x by some small quantity epsilon, but it's a completely new function. And then we defined the variation of y. So the idea of varying the function y as y bar minus y, and so this epsilon phi of x. All right, so y bar is y plus delta y. Right. And we also saw then that delta y prime, which is delta of dy by dx, we showed that that's the same as d by dx of delta y. And that's going to be epsilon phi prime of x, right? Delta y is this thing here. If I take the derivative with respect to x, epsilon doesn't depend on x, then I get phi prime. So let's remember these, as we'll use them very soon. So let's start with stationary value of an integral. Where the integral depends on a function L that itself depends on y, the derivative of y, and then x as well. Okay? So let's calculate the variation of the integral. So that's delta of the integral from a to b of L that depends on y, y prime, and x dx. And we also saw last time that the delta can come inside of the integral, right? So that's the same as the integral from a to b of delta L y, y prime, and x dx. So the question is, what does it mean to delta L? So it's the variation of L. How does L vary when you vary the y's and the y primes? Remember, x is the independent variable, and delta x is always 0, right? So what do we mean by delta L? Well, what we mean by delta L, just like we do here, right? Delta y is y bar minus y. So delta L is going to be L bar minus L. So what is L bar? Well, it's L evaluated at the varied values of y and y prime. So it's L evaluated at y plus delta y, y prime evaluated at y prime plus delta y prime, and of course x, it's not plus delta x because delta x is 0. And then it's minus the L evaluated at y, y prime, and x. Okay? So that's the key definition for delta L, or what we mean by delta of a function of a function. Okay? So let's look at this term here. And let's do a Taylor series about L evaluated at y, y prime, and x. Right? Because the delta y and delta y prime, in principle, can be infinitesimally small because they have this epsilon in it, and we'll make epsilon go to 0. Okay? So what is the Taylor series of L evaluated at y plus delta y, y prime plus delta y prime x around the central value? So L at y plus delta y, y prime plus delta y prime, and x, we only consider the first term in the Taylor series, right? Is going to be the term above which we're doing it. So L at y, y prime, and x, and then plus the derivatives times each of the variables. So it's plus di L by di y times delta y plus di L by di y prime delta y prime, and then in principle it's also plus di L by di x at delta x. And that term, of course, is 0. So this is just the first Taylor series expansion, right, about y, y prime, and x. And so this is the the distance away from y, and this is the distance away from y prime. And so the Taylor series has this form. So that gives us delta L. So delta L is this term which we just evaluated minus L. So the first term just cancels, and you get delta L is di L by di y delta y plus di L by di y prime delta y prime. Okay? And that's, of course, the chain rule that we've already derived earlier. Remember, in an earlier lecture, we actually looked at the variation of a function that depends on multiple functions, and we found exactly this. All right, so I'm just redoing the derivation. So that means our integral, the variation of the integral, is the integral from a to b of di L by di y delta y plus di L by di y prime delta y prime. And so we can do all the math now with the deltas, but if I were you, I also wouldn't quite be convinced yet on how to do the math with the deltas. So it seems a bit hand-wavy. So let's go back to the epsilons and the phi's that we've already defined. So that's the same now. Recall, delta y is epsilon times phi of x, right? And delta y prime is epsilon times phi prime of x. We'll put that in here. So that gives us the integral from a to b dial by dy epsilon. Oops, why is it moving like this? Dial by dy times epsilon phi of x, just substituting in, plus dial by dy prime epsilon phi prime of x. And the whole thing is dx. Okay, so the epsilon, of course, doesn't depend on x, so it can actually come out of the integral, right? And then let's ask ourselves again what we're trying to do here. We're trying to find a value where I is stationary. So as you make epsilon smaller and smaller and you vary the function y about its value that causes I to be a minimum, you want the integral to stop changing. So what we want is that d by d epsilon of delta I equals 0. That means that I is stationary for y of x. So we're trying to find y of x that makes I stationary. So a minimum or a maximum, but essentially that I stops changing rapidly in the vicinity of y of x being the correct function. So we vary y of x using this epsilon parameter, and we want this epsilon parameter to be equal to 0 when we have the right y of x, right? So that means this variation delta y stops changing for the right parameter, for the right function y of x, which is when epsilon is equal to 0. So this d by d epsilon of delta I, I'm sorry, is, so this is delta I, right? The whole integral has an epsilon in front of it. So that's the same as delta I over epsilon. And that's equal to now the integral a over b of dial by dy phi of x plus dial by dy prime phi prime of x. And that's the thing that we want to equal 0. And so again, the question is to find y of x so that this thing is 0. So in the end, we have to obtain an equation that tells us something about y of x. So how do we go about this? So what we'll do is we'll start with this term here, the second term. And we'll integrate this second term by parts. Right, so the integral of a sum, of course, is the sum of integrals. So we'll integrate this by parts. So we have the integral of a to b of dial by dy prime phi prime of x dx. So the reason we're going to integrate this by parts is because this is d phi by dx. Note that this is the total derivative with respect to x, and this is some derivative with respect to y, which is a function of x, and it's hard to deal with. But this is the total derivative with respect to x, phi prime. And so we can integrate it by parts. So if we integrate it by parts, the first term that we get is phi of x times dial by di y prime, right? And that's going to be evaluated between a and b. And then it's minus the integral phi of x times dial by di y prime dx, right? So that's integrating that thing by parts, right? You just remove the derivative from the phi of x, and then there's the part that's integrated out trivially, and then there's a part that remains an integral. Okay? So now the interesting thing is, what is this thing here in square brackets equal to? So remember, something that I didn't emphasize to you is that think about the problem of the bead falling down the wire. And we're changing the shape of the wire. That's changing the function y of x that we're trying to discover. However, when we change the function y of x by adding an epsilon phi of x, we're constrained to force that function to stay between a and b. So at x equals a and at x equals b, the function y bar of x has to equal y of x. So the variation, this phi of x, has to be 0 at the endpoints a and b. Otherwise, we're allowing any wire anywhere in space. But we've explicitly said that we care about a definite integral between points a and b, so we fix the ends of the wires. And so it's important to note that phi evaluated at x equals, xa, I don't know why it keeps changing. That's got to be the same as phi evaluated when x is xb. And that's got to be 0. So the variation at the endpoints has to be 0. It contains a phi of x that's evaluated and phi of x. Because phi at xa, I don't understand how OneNote works. Why does it change by itself? I apologize. Okay, so if we go back to our integral now, so we've evaluated this term here by parts, and so we can substitute it back in. So the first term was unchanged, so that's dial by di y phi of x. And now this term here has a minus, and so that's minus phi of x times dial by di y prime. And actually, sorry, that's a mistake. And that as well. The iteration by parts, of course, requires that this needs to have a d by dx in it. Right, when you integrate by parts, so here you have one function which is dl by dy prime times another function which is the derivative with respect to x, phi prime. So when you do it by parts, the first term is this, the phi prime function integrated, so that's phi of x, times the other function unchanged, minus the integral of phi of x times the derivative with respect to x of the other function. So I forgot this d by dx term here. So now writing this out correctly, our integral becomes di L by di y times phi of x minus phi of x times d by dx of di L by di y prime. So that does not seem more simple, right, than we had before. But actually it is. And so if I write out, both terms have a phi of x in them, so I'm going to take the phi of x out. So I have phi of x times di L by di y minus d by dx of di L by di y prime. And that's got to equal 0. And so let's think about this integral here. We want to find the function y of x so that this integral is 0. So that means this integral must be 0 no matter what choice phi of x we use. Remember, phi of x is just a tool that allows us to change the function y of x around the value that's correct. So since we can choose any phi of x, because this is only equal to 0 with the correct y of x, so phi of x is completely arbitrary. And so this integral must be true regardless of what choice we have for phi of x. Phi of x is this tool that allows us to change y. And so this must be true for all phi of x. So if this is true for all phi of x, it means that the term in square brackets must be identically 0. And that's the key result, is that di L by di y minus d by dx of di L by di y primed equal to 0. And I like to write this in the other way around. So since it's equal to 0, I can swap the two terms, right? I like to write this as d by dx of di L by di y primed minus dl di L by di y, sorry, equals 0. So this is a condition on the function y of x. And this is a very important equation, which you'll eventually know by heart. It's called the Euler-Lagrange equation. So remember, our problem is that we have a function L that depends on the function y and y prime. So all we need to do to solve for y is to take the derivative of L with respect to y prime. It's a partial derivative, so it's easy to do. And then we differentiate that with respect to x. And then we take the partial derivative of L with respect to y, subtract the two and equal to 0, and that gives us the differential equation for y of x. So this typically gives us an equation d squared y by dx squared equals something. So this will give us an ordinary differential equation for y of x. And of course, we know how to solve ordinary differential equations. And so this is a very important process, and it forms the basis for all of classical mechanics, is this Euler-Lagrange equation. This, in fact, we'll see when we do mechanics, that this is the equation of motion. Okay. So let's generalize a little bit and change notation. Let's do a new page. So in mechanics, we have a bunch of generalized coordinates, right? Qi of t. And those Qi of t's are what we want to solve for, right? That's the coordinates of the system. So they are like the y's of x. So in general, we'll have a function L, and it will be a function of Q1, Q2, Qn of t. It will also potentially depend on the velocity, so depend on Q1 dot to Qn dot of t, as well as time, right? And so the goal will be to find Qi of t. So this is the same thing as if the Lagrangian L depended on multiple functions y and y primes that depended on x, except now the independent variable is t. And so what you get in this case is you get one equation, you get one Euler-Lagrange equation per degree of freedom. And so then you'll find for each I, you'll have an equation d by dt, di L by di Qi dot minus di L by di Q I equals 0. All right, for each I. And so that's easy to convince yourself that you get one equation per I. If we go back to the derivation that we just did, our delta L here, right, it's going to have one term. So here there's only one y, right? If I look at the, I don't know if you guys can see my pointer on the underline where I'm talking. Oops. So there's a di L by di y, and then there's a delta y and a di L by di y prime delta y prime. If there was a second y, so y2, there'd be another sum, and there'd be a di L by di y2 delta y2 plus a di L by di y2 prime delta y prime. And so you'd be able to group all the y's of the same index together. And then for each of those groups of the same index of y, you can integrate the second part by parts. And so then it's, again, a sum of integrals, right? And then that total sum has to be 0, so each term in the sum has to be 0. And eventually you're going to get one of these equations for each of the y's. And so if L depends on multiple functions, Qi, Q1, Q2, Qn of t, Q1 dot, Qn dot of t, and t, then you'll get one Euler-Lagrange equation for each degree of freedom. So we'll do one special case now that simplifies, and then we'll go back to y's for this example, and then we'll go back to q's. So let's do a special case. when L does not explicitly depend on X. Okay, so that means that L is a function of Y and Y prime only. Then what we'll see is that this Euler-Lagrange equation simplifies. So remember, L satisfies the Euler-Lagrange equation. So d by dx of di L by di Y prime minus di L by di Y equals 0. So it satisfies L, but L has this special case where it doesn't depend explicitly on X. So it depends implicitly on X because Y and Y prime of X obviously depend on X. But explicitly, so the partial derivative is 0. So consider the following identity. So it'll be apparent in a second why we want to consider this, but consider d by dx of y prime times di L by di Y prime minus L. All right. So let's take this derivative. So the first term is multiplication of two terms that depend on X, right? Implicitly. So I have to use the product rule in the first term. So that the d by dx of y prime is y double prime times di L by di Y prime. The second term is y prime d by dx of di L by di Y prime. And then it's dl by dx, right? So let's rewrite the first two terms and leave them as they are. It's y double prime di L by di Y prime plus y prime d by dx di L by di prime. And let me expand the dl by dx in terms of partial derivatives. So that's the same as di L by di Y times Y prime plus di L by di Y prime Y double prime plus di L by di X, right? Now we split, so there's no confusion in how I went from this term to this sum of three terms, right? We did that in a previous example. Like why this term only has a di L by di X and it doesn't have an X after it. That's because the X after it would have been the dx that's dividing out the dl here. Okay? So we explicitly said that this is 0, right? That's what we set up here. So if I continue writing this out, now you'll notice that there's two terms that cancel. This term here cancels this term here. So there's a minus sign here, right? So I have y prime times d by dx of di L by di Y prime minus di L by di Y Y prime. And let me factor out the Y prime. So I have Y prime times d by dx of di L by di Y prime minus di L by di Y. Okay. Now, this term in parenthesis should start to look familiar. It is, in fact, the Euler-Lagrange equation, right? It's d by dx, di L by di y prime, minus di L by di y. So if, as we said, because so far this is just an identity, but if L satisfies the Euler-Lagrange equation, then this term is equal to 0, right? Because the Euler-Lagrange equation is precisely that this term equals 0. Okay, so why is that interesting? That means this whole thing here that we started with, this sort of random expression that I introduced, is equal to 0 if L satisfies the Euler-Lagrange equation. Well, why is it interesting if this thing equal to 0? This is the total derivative with respect to x of some function, right? The function being y prime di L by y prime minus L. So if the derivative with respect to x of some function equals 0, it means that that function equal a constant, right? And so, of course, that's the key result here. Since this derivative equals 0, that means that y prime di L by di y prime minus L equal a constant. And it'll be about 4 or 5 weeks before we realize why this was important. But we've done it on the mathematical side of things. Okay, what we'll find is that this, when L is called the Lagrangian, this expression here actually equals the total energy. And so this is, in mechanics, will become a conservation of energy. But for now, it's just a mathematical curiosity that when L does not depend explicitly on x, so that term canceled, or was equal to 0, then it turns out this quantity here is a constant. It's called the Jacobian integral, but let's only call that in mechanics, so we don't need to mention that here. Okay? And so that this is now a first order differential equation. If you do the math, you'll find that this is an equation for di y by di x equals something. And that's a first order ODE for y. Our problem is always a matter of solving for y that minimizes the integral of L. And the Euler-Lagrange equation gives us a second order ODE for y. So that's why when L does not depend explicitly on x, we can use this shorthand thing, which will give us a first order ODE for y. Okay. Yeah, so then I'm going to skip the next section in the notes because I've sort of tried to explain it. The next section in the notes is the case when L depends on multiple functions, y1, y2, etc. And the gist of it is that you get a term for each function, and each function then obeys the Euler-Lagrange equation. So we all. Yeah. So this result here is then derived in the next section when L depends on multiple functions. And I'm not going to do it here in the class so I can finish this chapter. But if L were a function of multiple functions, y1 to yn, y1 prime to yn prime, and x, but not x because it's the case where di L by di x equals 0. the result that you get, and the math is simple, is that the sum I equals 1 to n of y I primed die L by die yi minus L equals 0. But it's essentially the same derivation that we just did, except that you have to put i's on all the y's, and then you can group them together, and you'll find something like this. Okay? 2, 3, 4. So I want to talk about the stationary value of an integral with an auxiliary condition, or subject to constraint. And now I'm going to use q's so that we're more familiar with classical mechanics instead of y's. Instead of using y of x, I'm going to use qi of t. All right. And so this is section 2.7. So this is the stationary value of an integral subject to constraints. Constraints. So again, we have the integral I of L with Q1, Qn, Q1 dot, Qn dot, T, dt now equal to 0, subject to the constraints. And the constraint equations we'll write as we did before. We'll have some function of the Qi's, the coordinates, and we'll have k such equations. So again, the q's can be generalized coordinates of a system, and maybe those generalized coordinates are constrained. So you could eliminate the sum of the coordinates in favor of the others, right? Because these are functions relating the q's to each other. So presumably one can write q1 in terms of q2 to qn and remove q1 from the whole problem. But maybe q1 is important, or maybe there's no good choice of why you should eliminate q1 and not q3. So maybe you actually do want to keep all the qn's, but you want to include the constraints in your variational problem. So that's just like the assignment question that we were discussing for assignment 1. The 4 balls are constrained by the rods, and instead of eliminating all of the coordinates of the balls, maybe we want to keep in the constraints of the rods as additional, we call auxiliary conditions. So I've been calling them constraints because that's the language of mechanics. In the language of math, they're called the auxiliary conditions. All right. And so you may remember from last time, when we're finding the stationary value of a function subject to constraint, we use this method of Lagrange multipliers. And the beauty of that method, of course, is that it keeps all the variables on the same footing, and it turns out it also works for the problem of stationary values of integrals. So we know that delta I delta I is 0. And so the delta F1 is going to be equal to all the delta F's, and be equal to delta Fk. That's going to be equal to 0. Right? So I can again construct a thing that's equal to 0 plus 0 that's still going to be 0. So let me construct delta I plus lambda delta F1 plus lambda delta F2 plus lambda delta Fk, lambda k delta Fk. So let me consider the integral I that's equal to the integral of a to b of L of the q's. Q1 dot to Qn dot t dt plus the integral of a to b of lambda 1 delta F1 plus lambda 2 delta F2 and lambda k delta Fk dt. That's also going to be equal to 0. So what do we mean by delta F1? And we've done this before. Remember, F1 is a function of all the q's. So what does it mean to vary delta F1? So again, we apply the chain rule. And delta F1 is di F1 by delta Q1 plus di F2, oops, di F1, sorry. That's a, mistake over there. Delta F1 is di F1 by di Q1 delta Q1 plus di F1 oh, what happens? Alright. Having some problems with one note here. Delta F1 is di F1 by di Q1 delta Q1. My computer is going crazy. I'm going to write it on a different line. Delta F1 is di F1 by di Q1 delta Q1. I apologize for the technical difficulties. Di F1 by di Q2 delta Q2, etc. to di F1 by di Qn delta Qn. You can write that for F1, F2, all the way to Fk, right? So this part here, the first part of the integral, we already saw that it leads us to the Euler-Lagrange equation, right? And so effectively what we're going to get is I equals the integral from a to b of d by dt delta di L by di Qi dot minus di L by di Q. Right? That's this first term of the integral by di Qi. And there's going to be a term like this for each I, right? And so there's going to be a sum over I of these terms here and each of these terms was multiplied by a phi of x, or an epsilon phi of x, and that's the same as a delta qi. Right? So the first term, we saw that by integrating by parts, we can write it this way, and we can factor out the phi of x, which is the delta qi, and so we can write this as a sum. The second term, this term here, right? There's the delta f1, right? Is this sum here, di f1 by di q1, delta q1, etc. So the delta f1 is going to have a delta q1 in it. The delta f2 is going to have a delta q1 in it. And so each one of these terms has a delta q1, delta q2, etc. Right? So that's also going to be a sum of the n lambda 1 di f1 by di qi plus lambda 2 di f2 by di qi plus lambda k di fk by di qi in front of the delta qi, right? So for each of these terms, I've now grouped them instead of by all the f1s and all the f2s, I've grouped them by which one goes with which qi. And so it's a sum from I equals 1 to n of these terms for each of the qi's. So qi, qi. Okay? And so now we have this delta qi here, right? That's the epsilon phi term. So we divide the epsilon out, and then this term has to be 0 regardless of our choice of phi. Okay? However, the delta qi's are not independent, so we can't choose a different phi for all the q's. Right? Each delta q has its own phi function. Right? We're modifying each of these q's according to different functions phi. But we're not free to modify all of them. So they're constrained. So they're not all identically 0. So the terms in brackets are not all identically 0. So let's consider the last k terms of this sum, right? Remember, we have k constrained equations. So let's choose the last k terms. So let me write one term out of the sum. So we have d by dt times di L by, let's choose the last one, so that will be qn dot minus di L by di qn plus lambda f1 di f1 by di space, but it's di f1 by di qn lambda 1 di f1 by di qn plus lambda k times di fk. Why is it this? I don't understand what is wrong with this stuff. Oh boy. So I choose the last term of the sum, right? So it's an integral of sum, so it's a sum of integrals. And I choose the last term, so the nth term will be d by dt of di-L by di qn dot minus di-L by di qn plus lambda 1 di f1 by di qn plus etc. lambda k di f k by di qn. All right. And so we can write k of these equations. And so here we'll have the same equation with I equals n minus k. And now we can choose the lambda k's so that these n minus, or these k equations are 0. So we choose lambda 1 through lambda k to make these equal to 0. So now we've eliminated the last k terms from the sum by choosing the lambdas so that these terms are equal to 0. And then the remaining n minus k terms, so from 0 to n minus k, now those delta q's can be varied independently, and those terms are identically 0. And then what you find is that these terms now are all the same between the k last terms and the first n minus k terms. And that's, of course, the whole point of Lagrange multipliers. And so the final equation that you get, my computer will cooperate, is for all I, so any ith term, you find that d by dt of di-L minus di qi dot minus di-L by di q minus the term with the lambda is equal to 0, or plus the term with the lambda is equal to 0. And if I move them to the other side, so that's going to be the sum of, let's say, j goes from 1 to k of the lambda j di f by di qi, sorry. I'm going to fix the technical issues and redo this derivation in the summary next time because it's a little bit all over the place. And that's true for all I. Okay. So to summarize, you basically get a modified version of the Euler-Lagrange equation. So the Euler-Lagrange equation is this first term on the left-hand side of the equal sign. That's equal to 0 in the unconstrained case. In the case where you have constraints, it's equal to this minus the sum of the constraints times di f by di qi, and that's fj. Okay, I'll redo this derivation next time because I apologize, the technology is not cooperating. Any questions? Okay, so that'll be it for today. Thanks, everyone.